Thanks to organizers for giving me opportunity to present my work here. So, my work is basically cover time of stochastic search process under resetting, and this work is done with collaboration with Professor Sanjib Sabhapandit, and this is an ongoing work. I will just show the preliminary results. So, what is cover time? Basically, before starting this, just plan of talk is introduction and some previous results, and then my work and then conclusion. Okay, so before I start, I just would introduce the stochastic search processes. So the stochastic search processes are very natural events in day-to-day life. Let's say in macro events, let's say your key has been lost and you are searching this key in a stochastic manner, and you somehow you find and then again you don't find it again search and so on. Similarly, in the case of let's say in computer programming, there are bugs and you are finding searching this kind of things, and this is also a stochastic search process. So similarly, animals searching for food in biochemical reactions, there are cells sometimes like in DNA transcription, sometimes cells are reacting with reactive molecules. That is also search process. And similarly, so in all these examples, the time needed to discover this target is a limiting quantity, and consequently minimizing this search process is our actual aim, that how we can minimize this search process. So, when we take search processes, there is another term which is cover time. When the cover time is the minimum time needed by the random walk to visit all the sites at least once in a confined domain. So let's say there you can see that there is this. Okay. So there is different targets, and some searcher is searching this event, and you see that at some point of time it searches all the targets, and whenever it searches the last target for at least once, the process concludes. So this picture has been taken from this paper. So this is basically taken for a three-dimensional framework. So cover time in several stochastic search processes are often modeled by a single searcher problem for a simple random walk. In many situations, the search is for a confined domain and multiple targets, and these targets are scattered over entire domain. So these finding all these targets requires a exhaustive exploration, and our as I told that our aim is how to minimize that search processes. So there are some previous studies which says some mean cover time with lattice graphs and networks, and for complete graph L vertices it is this L log L. This is the paper, and similarly for different distributions for d-dimensional regular lattice where d greater than 2, for periodic boundary conditions, the scaled and converges as a Gumbel distribution. And similarly, you can the Gumbel distribution is found in for connected graph as well. So this paper shows that for different random walks in 3D, Brownian 3D, persistent 3D, and so on, you find a universal Gumbel distribution law for transient non-compact walk. But the problem arises when it is compact, recurrent, or marginally compact, particularly for the d is equal to 1. And the question is whether this is Gumbel follows the Gumbel law or something different. And similarly, when in this kind of processes whether the resetting can make these processes more efficient. So efficient means the search time decreases. So before I start with applying resetting, I just give a brief introduction. Then this is a diffusion process, and at some point of time there is a reset rate and it comes back to the original position or some resetting position. Let's say here it is 0, and the time has been taken from this Poissonian distribution, and this is the simple dynamics that goes to 0 with probability r delta t and 1 minus r delta t with simple diffusion. So this is the renewal equation, and the survival probability basically changes because of resetting with this expression. And there are several studies where it is found that mean first passage time decreases under resetting, but for higher resetting rate, it is not applicable. Then it again increases and goes to infinity. So my problem is the single random walk in 1D. There is a confined length 0 to L, and the particle starts from L by 2 initially, and it starts moving in as a random walk. And when both the sides, and this is reflecting boundary, and when the particle touches both the side at least once, and the process concludes. So here is the cumulative distribution function, which is a combination of three survival probabilities, where this says that when L is unhit, this is for 0 unhit, and this is for both are unhit, which will be a negative term. So in the Brownian limit, this probability distribution function is basically depends on 4 dt by L square. So the mean cover time can be calculated from this survival probability, where this R is equal to goes to T tends to infinity, and this probability distribution of Tc, where Tc is cover time, and it gives the mean cover time value as Laplace transformation of R is equal to R at S is equal to 0. So basically, we want to calculate this R at S is equal to 0. So these survival probabilities without resetting are quite known quantities, and we can compute this from the initial boundary conditions and so on, and using backward Fokker-Planck equation. And these are basically the Laplace transformation of these survival probabilities with non-resetting condition, of course, and there are two functions, G1 and G2. These can be computed as G1 lambda as this value, and G2 lambda as this value, which is Laplace transformation. Lambda is the Laplace variable. So now, using that protocol, how resetting changes the survival probability, we can find these survival probabilities of Laplace transformation of survival probabilities for the resetting condition, and we exactly can compute this mean cover time as universal scale scale reset rate as RL as the function of that RL square 4D. So this universal rescaled rate will give you a function, this function, and this function can be if you plot this function with the simulation value, you will find a universal expression for all the L's, whether it's for different L. And this universal rescaled rate RL square by 4D basically minimizes when at the value of 1.76979, which is another universal quantity for this system, single RW1D, and the value of the scaled cover time at that point of time gives 2.30 something, and you can see that it completely matches with this simulation results. So, so basically, we can find that for zero resetting, the search time is gradually decreasing for this optimal value until this optimal value, and again when we increase reset rate, and again increases this scaled cover time. So the process becomes, of course, more efficient after applying this resetting. So we get the probability distribution function with and without resetting. This expression is this analytical expression comes from this paper, and it matches with this computational results, and this dashed results are showing the computational, and this green one is this expression, and this is for this is the distribution after applying resetting rate reset. So this work is ongoing, and of course we have the conclusion that there is a certain reset rate where actually the search process reduces the cover time and the process becomes more efficient, and there is a universal scaled resetting rate for any value of L, and we have found the similar behavior, that mean cover time decreases for the resetting for a RTP particle in one dimension as well. So thanks to Sanjib, Sabhapandit, and thank you all for listening.
Questions? Since there is no question, let us thank the speaker.
Thank you. Thank you.